Assalamualaikum to Dr. Halimah binti Abdul Rahman. My name is Fatin Adana Aisha binti Muhammad Zafri, and my matrix number is CD240312. And I'm from Group 1 from Section 5. We are going to present superconductor materials. Introductions. Superconductors are materials with unique properties, including zero electrical resistance and the Meissner effect at portions of magnetic fields when cooled below a critical temperature. These materials enable extremely efficient electrical conductions and are indispensable for generating strong, stable magnetic fields. The development of high-temperature superconductors (HTSS) has expanded their potential applications, as they remain effective at relatively higher temperatures compared to earlier superconductors. Importance of superconductors. The first one is energy efficiency. They eliminate energy loss in electrical systems, improving power grids, renewable energy systems, and long-distance energy transmissions. The second one is technology applications. Superconductors are essential for devices like MRI machines, particle accelerators, nuclear fusions, research, and quantum computing. Challenges and future prospects. The primary challenges include the need for cryogenic cooling and the complex, costly manufacturing processes for superconducting materials. However, recent advancements such as near-room temperature superconductors suggest a promising future for applications in energy, transportation, and advanced technology. Superconductors hold immense potential to revolutionize energy efficiency and drive innovation for a sustainable future.
Hello everyone, let's talk about high temperature superconductors and how they could revolutionize electricity transmission. Superconductors are materials that can conduct electricity without resistance, eliminating energy losses. However, traditional superconductors require extremely low temperature to work, which demand expensive cooling system. High temperature superconductors, or HTS, offer a game-changing solution. Materials like barium, copper oxide, and bismuth strontium calcium copper oxide operate at higher temperature, making them far more practical. The ability of HTS to function at relatively higher temperatures reduces the need for costly and bulky cooling system. This makes them an attractive option for real-world application. HTS materials can transform power transmission by enabling lossless electricity grids. They are also key to advancing technologies like magnetic levitation for high-speed trains and other energy-intensive innovations. With their efficiency and cost-saving potential, HTS like YBCO and BSCCO could pave the way for widespread adoption of superconducting systems, shaping how we generate and use energy. Let's start with iron-based superconductors, such as iron selenide and iron arsenide. These materials are gaining attention due to their relatively high critical temperatures and potential as cost-effective alternatives to traditional high-temperature superconductors. While their critical temperatures are lower than those of cuprates, iron-based superconductors stand out for their ability to operate under higher magnetic fields. This makes them suitable for powering electrical grid and devices. Additionally, their affordability and versatility make them an attractive focus for ongoing research and development. Next, we have magnesium diboride, a material with a critical temperature of around 69 K, while this is lower than that of some high temperature called superconductors. It is easier to cool, making MgB2 practical for a range of real-world applications. MgB2 is particularly promising for power cables and MRI systems. Its combination of moderate cost, favorable superconducting properties, relatively simpler cooling requirements position it as a key material for improving the efficiency and scalability of superconducting system. Next, we have magnesium diboride, a material with a critical temperature of around 69 K, while this is lower than that of some high temperature called superconductors. It is easier to cool, making MgB2 practical for a range of real-world applications. MgB2 is particularly promising for power cables and MRI systems. Its combination of moderate cost, favorable superconducting properties, relatively simpler cooling requirements position it as a key material for improving the efficiency and scalability of superconducting system. Both iron-based superconductor and MgB2 have unique strengths that can revolutionize technologies like power transmission, medical imaging, and more. Their affordability and adaptability make them excellent candidates for advancing the efficiency and accessibility of superconducting system. In summary, iron-based superconductors and magnesium diboride highlight the diversity of materials being explored to enhance superconducting technologies. With ongoing research, these materials could pave the way for cost-effective, scalable solutions in power grids, healthcare, and beyond.
Hi, my name is Ahmad Azwir Hamzah. My matrix number is AD220003, and I'll be presenting about processing manufacturing. So, types of superconductors and their manufacturing. Superconductors are classified into two main categories. Number one is low temperature superconductor, LTS, and number two is high temperature superconductor, HTS. Processing of low temperature superconductors. The processing of LTS materials involves the following steps. There are 4 steps. Number one is alloy preparation. Number two is wire fabrication. Number three is high heat treatment. And last but not least, encapsulation. So this is all for low temperature superconductors. We're moving on to high temperature superconductors. HTS materials demand more sophisticated process due to their complex crystal structure and precise composition requirements. There are 4 steps also in this process. Number one is powder synthesis. Number two is tape of wire fabrication. In tape of wire, in this process, powder in tube PIT process is used and coated conductor process. For the following step is crystallization and orientation, and number 4 is encapsulation and protection. So that's all for me. How was that?
My name is Desmani Diana Anzi. So I will explain selection of suitable materials. The selection of suitable superconductor materials is crucial for revolutionizing the way we generate, transmit, and store electricity. Superconductors are materials that can conduct electricity with zero resistance when cooled to very low temperatures, potentially eliminating energy losses during electrical transmission. The future of electricity will greatly benefit from advances in superconductor materials. Let's explore some promising candidates and the factors that make them suitable for this purpose. Okay, so comparison of each material and decision making. First, high temperature superconductors. One of the most promising classes of superconductors for the future of electricity are high temperature superconductors such as lithium barium copper oxide and bismuth sinterium calcium copper oxide. These materials have critical temperatures much higher than traditional superconductors, making them easier and cheaper to cool, as they only require liquid nitrogen 77K instead of liquid helium. Second, iron-based superconductors. These materials offer several advantages over traditional copper oxide. superconductors, including lower production costs and better mechanical properties. Third, organic superconductors. Another promising area of research is organic superconductors, which are made from conducting polymers. These materials have the advantage of being lightweight, flexible, and potentially cheaper to produce. Okay, factor to consider in the selection of superconductor materials when choosing suitable superconductors material for the future of electricity. Several key factors must be considered. First, critical temperature. Second, cost of production. Third, mechanical strength. Fourth, ease of fabrication. And fifth, stability and durability. By choosing organic superconductors as our material, superconductor electric and organic superconductors are the most suitable materials than the others. Here are the main advantages of organic superconductors. First, organic superconductors are typically much lighter and more flexible than conventional inorganic superconductors. Second, organic superconductors can often be synthesized from cheaper and more abundant materials compared to traditional superconductors, which require complex manufacturing processes. And third, organic superconductors can be synthesized from a wide variety of organic molecules and polymers, allowing for significant tuning of their properties. And fourth, organic superconductors often operate at relatively low temperature but still significantly higher than traditional superconductors. Some have critical temperature in the range of 20K to 30K, which, although still requiring cooling, is much more.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ashis Kandam Sharizal, and its number is CD240244, and I will be present about the conclusions. From our revolutionary potentials, superconductors have the unique ability to eliminate electric resistance and control magnetic fields, making them a game changer for energy, technology, and research. The applications is they enable more efficient power systems, advanced technologies like quantum computing, and are crucial for renewable energy and particle accelerators. However, there's a challenge in doing this. There's widespread use is limited by high costs, complex manufacturing processes, and the need for the cooling systems. And the advance is that high temperature superconductors like YBCO and BSCCO are improving accessibility, while organic superconductors offer cheaper and more flexible solutions, especially for portable technologies. For the future look, if room temperature superconductivity becomes a reality, it could be completely transform global energy transmissions and innovations across the industries. So the conclusion here is that superconductors are not just a scientific curiosity. They are critical to the future of cleaner, more efficient energy and cutting edge technology. That's all from me. Thank you.